Okay, so in this video I'm going to be going through 3 bending moment questions, bending stress questions in the Kirkland textbook, Engineering Studies, a Definitive Guide, Volume 2. We've got exercise 1.11, 1.12, and because they wanted to fit this one in between, 1.16. It's confusing, but that's the order. Now, what we're going to do, you notice that what I've done is I've taken these word questions and I've written the data. I do suggest that it's actually a really good idea to write in the HSC, to write and present your data like this. You don't have to, but this is something that was taught to me, and I at least want to be somewhere on the record to say that I've told this to students. So what I've done is, I'm not going to read out the specific wording of the question, that's available. But what I've done is I've said, okay, the depth of the beam is 300. They've said the BM, so the bending moment, is 25 kilonewton meters. And then we have how do they raise it? They say the second moment of area is 3.4 times 10 to the negative 4 meters to the power of 4. Now, we're going to work with that and we're going to go forward. So the first thing we need to know is what is the formula for working with bending stress? Now, I've said this a couple of times, I'm going to say this really quickly. There's 3 things that you need to know in this subject to not embarrass me. You need to know that concrete is made of cement and aggregates. The second thing is you need to know is that stress equals force over area, except, I've got an exception in a second, that's 2A, but I also have a 2B. And the third thing is you need to know that mild steel has 0.3% carbon and a yield stress over 300 megapascals. Now, I said that stress equals force over area. Stress equals force over area, except for bending, right? The rule 2 is this, rule 2B, or not 2B, right? Rule 2B is this, bending stress equals my over I. Now most people find that pretty easy to remember, so there's 3 parts to this. Bending stress, sigma B, equals M times, now I try to avoid using the times symbol because it can be confused, right? We mix up an X and the multiplied. But so I'm going to put it up here just so that we don't confuse it with an X. Multiplied by Y, all divided by I. Now, I like to show people that I've gone to uni, so I might write it instead like this. Sigma B equals the maximum bending moment, which I might write as M star, or I might write it just as M max. That's typically what I write now, is I write M max, multiplied by, I'm using an asterisk there, which is confusing even for me. I don't know how a good symbol to write multiplied by. Okay, so we're going to do that, multiplied by Y bar, which is a term I would use at uni or at work, and IXX. Now we can just use I, but I like IXX. It's for you that you don't need to worry about what the difference is. I just like this symbol. Occasionally you'll see IXX in your in HSEs. Occasionally they'll have IXX. The idea is that the I value, the second moment of area, can be different depending on if the beam is standing or if it's laying flat. Now, later we'll talk about why that's relevant, why that's important. I have other videos where I talk about that already if you want to learn more, if you go through my other videos. But the idea is that when you're building a house, right, so those of you who are doing construction, when you're putting a bearer or a joist in, which way do you put the 2x4? Do you put it standing up or vertically or horizontally? Good answer. Okay, so I will tell you that when you're building a house, right, you have your bearers, your joists, your rafters, right, whatever you're putting in, you always make sure that the beam, this piece of the 2x4 or the 90x45 or whatever you're using, you might be using 70x35 or whatever it is you're using these days, that member it always stands. And I remember when I was doing decking, when I left high school, I worked in construction for 2 years. And my first thought, I was working through high school as well, but I remember my first thought is, wouldn't it just be so much easier to nail these in if we could just lay them flat? And my boss said to me, no, they're not as strong. So we have to put the nails in through the side to nail them to the bearers, rather than because you usually can't get a nail all the way through the 90mm, maybe some cases, but most of the time you'll nail from the sides, right? Whereas it'd just be so much easier if it laid flat. And the reason for that is we want a big D, right? The bigger the depth of the section, the stronger it's going to be, right? So the point there is we want the big D, the bigger the depth of section, the stronger it's going to be. The breadth doesn't really matter. Now there is a point. There is a point where if we had a member that was 5 times longer than it was wide, right? Or the depth was 5 times the breadth. Then this is the convention, right? We use D and B. That's the convention. There is a point where it can be so slender. The section is so slender that it might want to buckle on itself. It might want to collapse. But up to a ratio of at least 2 to 1. We much rather have the depth be big than the breadth be big, right? We get a lot more strength in bending. In bending, we get more strength when we have big D. Where if it's in compression, if you have a post, this is why we see posts will usually be 4-inch square, right? 90 by 90. Because in that case, with compression, with a column, it needs to be strong in every direction. But with bending, we know that we're applying the load from the top. We want a big D. Okay, so that's why we have IXX. I won't go into too much more detail, but just say that the x-axis is this axis, the y-axis is that axis. We don't care about them in the HSC. We're never going to give you a question that talks about the IYY. I can't think of, there must have been, twice in my university degree where I ever used IYY. It is in the textbooks. I will show you that in a second. That steel codes, might as well show you now. Okay, so if you're buying, if you've got a rectangular section like this, it's pretty easy to calculate the IXX value, right? The second moment of area or the moment of inertia. We're going to use the term second moment of area, but you should be aware that if you see in really old tests, right? If you look in the 2001, 2002 test, there are questions that refer to it as the moment of inertia. That's why it's an I for moment of inertia, right? That said, for rectangular sections, really easy to calculate, right? And when you get to uni, you'll be calculating it. Even for I-beams, right, steel I-beams, you can calculate it. Maybe you don't want to calculate it, it's maybe a little bit time consuming, but you can calculate it. Whereas when you get to buying steel I-beams, they don't expect you to calculate it. They've all predefined. They already know what these values are. And you can look across this table. I'm not going to show it to the camera. I have in other videos. But if you look across this table, you'll be able to see the values. And I've bookmarked, because I needed this when I was at uni, right? I bookmarked across where I can find the IXX value and the IYY value. And you can see the IXX value is always much higher than the IYY value. The only reason the IY value is there is because in some situations the thing might be exposed to wind loads, or if you're using it as a column. It's there for a reason, but we, in this subject, we're only interested in the IXX value. Now, most of the time, you won't even see it written, right? I just want you to know, if you see the wording moment of inertia, or if you see this terminology, I want you to know what it is. Y bar, I don't think you really see that in the HSC, but I just find it's easier to help it stand out. The letter Y on its own, I think, just looks a little lonely. So you might see my notations around the place. That said, my over I think most people remember. I thought about for this, my thumbnail might be the me, myself, and Irene, right? That was sort of, when I was at uni, that was definitely the terminology we would think of. As there was a movie. See, this is a 20-year-old movie now. It had Jim Carrey in it. Anyway, me, myself, and I. Me, myself, my over I don't know. I never struggled to really remember this. The thing you got to remember is it's M times Y divided by I. That my is two separate things. Yeah, we're combining two separate things. But you can see how they're two first-person pronouns. Okay, now that we know that, what do these things come from? Well, the first one is M max, right? What is the bending moment that we're interested in? That's what M stands for. M stands for bending moment. Now, in some cases, the bending moment will be given to you. It can be given to you, but often we'll be given a load diagram and we will calculate the bending moment. How do we typically find the bending moment? We did it last lesson. We talked about it before I started recording. It's a diagram, it's got 3 letters.
Shear force diagram.
Not the shear force diagram, but it's close. We use the shear force diagram to calculate another diagram. The bending moment diagram. So from the bending moment diagram, we get this value. Okay. The next one we have to look at is, what is the Y bar? Where do we get the value of Y?
From halfway off the depth.
Okay, half the depth. Often it's going to be half the depth, right?
From the max to the neutral axis, isn't it?
Yeah.
Sometimes it's going to be D on 2. I'm putting a question mark to say it's sometimes that, not always. But the most correct answer is to say that we get the answer, the distance is, I don't want to write it out. I wrote it last time. It's the distance from the neutral axis to the extreme fibre. Yeah? The extreme compressive fibre or the extreme tensile fibre. Yeah? If the neutral axis is in the middle, it's not going to matter. We're going to see that in a second. We'll talk about that in a second. Lastly, we have IXX. Now I said that for rectangular sections, we can calculate it easily, but we don't need to. In other videos, I've talked about how you can do that, but I'm not going to go into it. I don't even want to confuse you with telling you how to calculate IXX. Because in the HSE, IXX will be given to you. The second moment of area, the moment of inertia, will be given to you. Now, for I-beams, you can calculate it. Obviously, like the founders didn't, they didn't come down from the heavens and say, oh, here's all the IXX values. That didn't happen, right? We can calculate them, right? If we have an I-beam or a T-shape, we can calculate the second moment of area. But if you're buying steel off the rack, they're going to be given to you. You can look them up on a table. So, as far as the HSC is concerned, that value will be given. Okay, so let's work our examples, right? We're going to do Ex1.11. Okay, we're going to plug in these values into the calculator. So what we're going to say is the sigma b equals, what's our value for m? 25, okay? Now what is the unit? Kilonewton meters. Okay, now it's important that in this case, right, I want to highlight a point. We've talked before about the grease units, right? What are the grease units? We go together like
millimeters and megapascals.
Millimeters.
Squared.
Yeah.
And megapascals.
Millimeters and megapascals. They go together. So if we have a megapascal equals 1 Newton divided by a millimeter squared, yeah? Or we can have 1 Newton divided by a meter squared equals a Pascal. In this case, this is really hard. The I value, right, the second moment of area, the moment of inertia, is really hard to convert. Right, we don't want to convert. It's really hard to convert. So if they've given us an answer in meters, we want to make sure that everything we use is not, just so that when I talk about grease units, we know this is the grease units, right? I'm going to put the little music notes to say that's our grease units, right? Grease as in the musical. I actually hate the musical Grease, but anyway. So we're going to use everything in meters, but kilonewtons is not right. So we need to multiply that by 1,000. I'm not going to write 1,000, I'm just going to write 10 to the 3. Okay, what is our Y value? 150, is that what we're writing down? Can't write 150, right? Because 150 is in millimeters, and what units are we using? Meters, right? Copeland loves meters, right? Copeland loves meters. This is a Copeland thing, right? I'm going to come back to that in a second. But, so to convert that into meters, now what we'll see is that those will cancel out, right? That makes pretty, we can see if we multiply by 1,000 and 10 to the negative 3, they're going to cancel out. Okay, another way we could write that is we could have written that as 0.15, but I find if we write 0.15, people get confused, right? I find that because often people will write 50 millimeters as 500 millimeters. That's the big one, especially if you do chemistry. Right, 50 milliliters, people are always writing that down as half a litre, always, right? Now, we then have our I value, or our second moment of area, which we're going to say is 3.4 times 10 to the minus 4. Now, if we put that into the calculator, what answer do we get? Okay. 110,294,118. Is that what you guys got?
Yeah.
Now that answer is in pascals. So what we're going to do is we're going to take 2 commas away. Yeah, I watched this movie called Finding Forrest where he called the rich kids 2 comma kids. 1 comma, 2 comma, because they had $1 million, right? Anyway. Now, some of you might have a textbook and you can check if that answer is correct, but it looks like a reasonable answer, right? What is the allowable bending stress of steel? I said there's 3 things you need to know to not embarrass me in the subject.
Above 300.
It needs to be less than 300. Yeah. So okay. So the yield stress of steel is above 300. So if this is less than 300, that means that the stress that we're asking this steel to survive is less than 300. Right? It can deal with 300, but if it's as long as it's less than 300, it's going to be happy. Yep. Why missed a comma? They've said it's 11.
This is 1.8.
Yeah. Oh, really? 0.8, so why are you doing that?
Yeah, they've said it's 11, not 10. So 25 times 150 divided by... Say it right.
Yes, I got that. What'd you say?
Oh, that's fixing this. Yeah.
I added an extra 0. Sorry about that. Yeah. 294. Yeah, this is where the decimal is. Sorry. Okay, I'll clean that up. So, I'll take a photo and then I'll move on. Feel free to skip if you're watching this on YouTube. Okay. I'm glad I checked. So, with my calculator I could have just divided by scientific notation, divided by 6 to get it into the unit, or divide by 1,000,000, but I did not. Okay, we're now going to do the next one, which is a weird number. We're going to do 1.16, but it's just the same idea. We're just going to plug in these same values. We've got bending stress equals, what's M? 12. Now remember it's 12,000 because it's kilonewtons, right? And then we're going to multiply by Y, which this time we're going to write as 0.14, right? And then we're dividing by 1.67 times 10 to the negative 4. Okay, now in the question they talked about the radius of gyration and the Young's modulus. I'm not going to go into that. If you want to look at that through the book, by all means do so, but I think that that's very, very low probability of being in the test, right? Radius of gyration. I personally, you do talk about Young's modulus when you're calculating deflection at uni, but I don't think I've ever used radius of gyration in any calculation at uni or professionally. So that's my experience, but it's in the textbook. Who am I to argue with Copeland? He knows a lot more than I do. I'm going to plug in some numbers, and I'm going to say 12,000 times 0.14 divided by 1.67 to the power of negative 4 equals, and now this time I'm going to divide by 1,000,000 because I don't want to get it wrong. Just checking out the right number of zeros, and I get 10.06. Okay. Now, I want to do the last one. The last one is the one I'm excited about. The first two, they're warm-ups. Now we're up to the big one. We're going to do exercise 1.2, exercise 1.12. So it starts over here, we have some data, and it continues over to there, right? So what we have is, we've been given this I value, right? This second moment of area, or moment of inertia, right? Of 4.6 times 10 to the negative 4. And what I did is I wrote that number out because I don't like using meters The reason I don't like meters is, although there have been questions that use meters in the HSC, it does exist, right? Again, if you go back to 2001, 2002, they used to use meters. And Copeland loves meters, right? I have nothing against Copeland, but he loves meters. The thing is, this textbook, right, which is issued by the Australian Institute of Steel Construction, right, this is the standard that everyone uses. If you buy a steel beam, you're using this. Every single one of them has millimeters to the power of 4. Now, the question, this is a good point to say, what is a millimeter to the power of 4? Don't even worry about it, right? I have explained it in another video. If you want to watch that video where I talk about what is a millimeter to the power of 4, and I talk about how we're taking the second moment of the area. We're taking the moment of an area, and we're taking it again, right? That's how we have an area, right? An area is in millimeters squared, right? And we take the moment of it once, so we multiply by millimeters, it gets us to area cubed. We then multiply it by area again, by distance again, and when we multiply it by that distance that second time, that second moment of area, that gets us to millimeters squared times millimeters again, gives us 4 lots of millimeters, right? That's how we get to millimeters to the power of 4. I don't like to use meters, I like to use millimeters, right? Because I have always used grease units, right? I used grease units when I was working, I'd use grease units. Grease units are the way to solve this. Now, I'm saying that because all of the recent HSCs have given our answers in millimeters to the power of 4. Me, I find it really difficult to calculate, to convert these. Now, how do we convert it? Well, we started with meters, and I said, well, that was our decimal point, and we said that this was 0.4. That's right? That's the right number of zeros? Yeah, we're happy with that? That scientific notation is correct.
Yeah.
You'll tell me if it's wrong, yeah? Because I don't want to be wrong on the camera. That's everyone's really happy that that's the right number of zeros for 10 to the negative 4, right? Let me just type that in just to prove it, right? I'm going to type in 4.6 e 10 to the negative 4 gives me that number, right? 0.3024, right? The idea when you're doing scientific notation, I always think you count that first zero. That's how I count it. 4, 1, 2, 3, 4. Okay. Then what I did is just wrote out a whole bunch of extra zeros. And I jumped, you know how you move, sometimes you see maths teachers move the decimal place? I'm moving it in bunches of 3s. So, the thing is, we're converting to millimeters, but we're converting to millimeters 4 times. So, one conversion, right, because there's 1,000 millimeters in a meter. Another one, that's power to the power of 2, power of 3, power of 4. So what we then get is an answer, which is 4, 6, with how many zeros? 1, 2, 3, 4, 5, 6, 7. So I'm going to put in my commas again, right? I've got 1 comma, 2 commas, gives me 460 times 10 to the 6. We okay with that? Okay, that's how I proved it. We're going to see, right, if I'm wrong, it's going to be hilarious because I'm going to be wrong on camera. Maybe I'll burn the video, but we'll see how it goes. So turning over the page, we're looking at page 38. I've drawn the diagram up already to try and save some time on camera. Now, what we can do, there's 2 different ways that we can calculate our maximum bending moment. 2 different ways. One is I said in one very specific case, we're allowed to use this formula. We're allowed to say that M equals FL on 4. Yeah? Okay. Is that this case?
Yes.
Right? It's a symmetrical beam with a single load in the center. Yeah? That looks pretty good. It's one span. Even though we have these extensions over the side, they don't count because there's no forces there. We're not interested in that. So we can use this formula, right? So let's see what our calculation will be. What is the value of L? Now in another video, I ridiculously and embarrassingly, I only used half of L because I didn't remember to add these 2 numbers together, right? So L in this case, L is equal to what?
Length.
Yeah, which is equal to?
10.
Thank you. 5 times 5 equals 10. The length between the 2 spans. I wish that looked a little bit clearer. Okay.
Yeah.
I can do better than that.
That's wrong.
Even if I'm going to use another camera colour. I'll use blue. Where's blue? L equals 5 plus 5 equals 10 meters. The distance between the span. Yeah? Okay, so what we're going to say is we have 56 times 10 divided by 4.
140.
What is it?
140.
140. Okay, now that's going to be 140 kilonewton meters. Yeah? Now that's not the bending moment everywhere, that's the maximum bending moment, right? So I'm writing that down as M max. Now, we're going to prove that by drawing the diagrams. So we're going to draw the shear force diagram. What are our reactions? Now I need to write it down. What are our reactions? If it's 56, what are our two reactions? 28? Yep, sounds great.
28 upwards.
On both sides, because it's symmetrical. So, we had a beam, once upon a time, the beam went up 28. Then what happened?
Went down 56.
Down 56, and then across, and then back up 28.
Yep.
Yeah, down 56 there. Okay, and where did it end up? It ended up back to 0. Are you okay with that diagram? Okay, so now what we need to do is we need to find the area of these blocks. The distance here is 5 meters. So 5 times 28 equals?
140.
It's exactly the same value, right? And then we're at 140. Okay, and then we have to minus that same area, gets us back down to 0. Yeah, that's our bending moment diagram. Now, once we have our maximum bending moment, we can then just plug that number in. We can say the bending stress, equals 140. Now, I want to use millimeters to the power of 4. We're going to see if we get the same answer as Copeland. Fingers crossed. I honestly don't know. It could be a train wreck, right? Now, we're multiplying this by 1,000 because there's 1,000 kilonewtons, 1,000 newtons in a kilonewton, right? That makes sense? There's 1,000 newtons, yeah? So we're going to multiply it by 1,000. And then we're going to multiply it by how many millimeters are there in a meter? Okay, how many centimeters are there in a meter?
100.
How many millimeters?
1,000.
Great, we got that. Okay. Then we're going to multiply by what is our y value. Now this is the tough part, right? This is the tough part. Our y bar, we can choose to use our distance, our neutral axis is not in the middle. For this section, we've got a T section, our neutral axis is not in the middle. It could be 200 from this neutral axis to an extreme fibre, or it could be 100 newtons from an extreme fibre. Now, there has been a HSE question where they asked to find the compressive stress in the beam, right? There was a famous HSE question that asked to do that. But otherwise, if they're just saying find the maximum bending moment, well, in that case, what we're going to do is we're going to use Copeland goes through and he finds both, right? He uses 100 and then he goes and does 200. But what we have is a little rule to help us remember that if we're not sure which one to use, and they haven't given us any clues in the question, which one should we use, which one's likely to be critical? Which one's likely to give us a bigger stress? Remember, bigger stresses are critical, right? If you have a chain, you say that chain has got a lot of stress on it, right? That's more of a worry than if someone says, no, that chain's only got a little bit of stress on it. Okay, which we like to call big Y! Yeah? Okay. So, big Y. So we're going to use that value. We're going to use this one here, what we call big Y. We're going to use that as our value. We could use both, but we're going to use that one. Now, we're using Greece units. We go together like megapascals and millimeters squared. So, we're going to use that. That's in millimeters. This isn't in millimeters squared, but we're still allowed to use it, right? We're still, even though our I value is not in millimeters squared, we're still allowed to use it. And we're going to write 460 times 10 to the 6. Sorry. I just realized I had an error there. I got ahead of myself. I'm going to go back to this line here. We had, how many newtons are there in a kilonewton? 1,000. How many millimeters are there in a meter?
1,000.
1,000. Okay, if we have 3 and 3, we can add those together.
Yeah.
Yeah? So what we could do is we're allowed to go, we could just get rid of this altogether.
10 to the 6.
and just write it as 10 to the 6, exactly right. Now, some people will have seen that I actually wrote 10 to the 6 on the board because I was getting ahead of myself, right?
Yeah.
And now, what I can do is I can cross that and that out. Yeah? And that is why the units are almost always given in 10 to the power of 6. I can't recall seeing a manufactured product, right, which gives a number to anything other than 10 to the power of 6. Okay, 140 times 200 divided by 460 equals. Now, what is my answer in? What units?
Newtons.
So force over an area. Megapascals is the answer. It's a Greece unit, as the kids are saying. We go together like megapascals and millimeters squared. Okay, what we get is an answer of 60.87 is the answer in the textbook. I rounded a little early. I get 60.86952522, just to show that I'm not just copying out of the book. Now, they go on and find the section modulus, or the, sorry, not the section modulus, they go and find the Young's modulus. I don't care, right? This part here, I don't care, right? You can learn that if you want, right? It's in the textbook. I urge smart kids should learn it, but for most people, it's not worth the effort. Statistically, it's so unlikely to be an HSC question that, look, I've already eaten 2 hats in teaching this subject. I don't want to have to eat a 3rd hat, but I think it's pretty unlikely. But by all means, I urge you all, read the textbook, right? I've set it for homework, you need to read the textbook and complete the answers. So here's the solution to that question, and we've proven that we can use millimeters to the power of 4. We've used that instead of the method that Copeland has. The reason I stress that is I really love Copeland's book. I think it's a fantastic book, right? If I only could ever use one textbook, it would be Engineering Studies, The Definitive Guide. That's a free plug, right? I have no financial affiliation with Copeland. But from a practical perspective and from a convenience perspective, knowing how to use grease units, because that's what this textbook gives all the answers in, and that's what the HSC is going to give the answers in, is just so much easier. It's unfortunate that these examples, they are in meters. Now, here's the thing. Next year, when you do the HSC, for all I know, they're going to give an answer in meters to the power of 4. What do you do in that situation? You just make sure everything is in meters. Yeah? If you use meters for I, you use meters for everything. If you use millimeters for I, you use grease units for everything. Yeah? That's the key. The grease units are the only time I can think of, right? And I've been doing this for a while. It's the only time where we really want to use anything other than the base SI units. Okay?